Good morning, students. In the previous class, we were discussing Young's double slit experiment and we have derived some equations. We found a relation between the phase difference and path difference of the waves that interfere. And then we also derived expressions or conditions for constructive interference and destructive interference. Today we will continue with Young's double slit experiment and we will derive equation for the separation between two consecutive fringes and fringe width. So let us begin. We saw that in Young's double slit experiment, there will be light from a single source divided into two sources with the help of two slits. Let me represent them as S1 and S2. We need a single source of light which is separated into two independent sources, because only then we will get coherent sources of light that meet, and on the screen we can see the interference pattern. So it is very important that we have to take the light from single source. Now the separation between these two slits is represented by the letter A. Now you have a screen at a distance D from the slit. So this is the center. So at a distance D, you have the screen on which we can see the interference pattern. So yesterday we discussed that if the light ray come from S1 and S2 and if their path difference is 0, when they meet at the center, what will be the type of interference at 0, at O? What kind of interference will be there? Will it be constructive or destructive?
Constructive.
It will be constructive interference, and we will get a bright light or maximum intensity at the point O. Now we will get dark, bright, like that fringes on the screen. Let us suppose at any point P we have a maximum intensity or we have constructive interference at a point P. Let the point P be at a distance xn from O. Okay, so xn means we get the nth bright fringe at a point P. So here suppose we get the central maxima or the zeroth bright fringe when n is equal to 0. Now if I go a little up, you will get the first bright fringe, then the second bright fringe, third bright fringe, etc. And at P, you will get the nth bright fringe. Or we say that the order of the fringe is n. So xn is the distance between the point O and P. Now what is the condition for the light ray to have constructive interference at point P? If S1P is the distance traveled by light that comes from S1 to reach P, and let S2P be the distance traveled by light from S2 to reach the point P. So what will be the path difference? The path difference will be S2P minus S1P. Okay. And what is the condition for constructive interference? The path difference should be equal to, yesterday we derived this equation. What is the path difference? Path difference is equal to n lambda, where n is the order. So if it is the nth bright fringe, it will be n lambda, the path difference. So we assume that at P we have a bright fringe. Now, what is the path difference? It is S2P minus S1P, right? Now, let me consider a perpendicular drawn from this point to S2P such that this point at this point B, the angle is 90 degree and BP is equal to S1P. So BP is the distance same as S1P. So this will become the path difference. So this is the path difference. This will be S2P minus S1P. Why? Because BP is equal to S1P and this angle is 90 degree. So this is the path difference. And let me take this angle as equal to theta. Okay. So we have a triangle here, S1, S2B. So look at the triangle S1, S2B. Triangle S1, S2B. So from triangle S1, S2B, we have sine theta is equal to, when I take sine theta, it is opposite side by hypotenuse. So opposite side is S2B. S2B means S2P minus S1P. So let me write S2B, which is the opposite side, as S2P minus S1P divided by the hypotenuse. Hypotenuse is S1, S2 because this is 90 degree. The side opposite to 90 degree is S1, S2. So that is equal to A. This distance is A. So what is S2P minus S1B? For constructive interference, it should be equal to n lambda. So I can write that sine theta is equal to n lambda by A, or A sine theta is equal to n lambda. So this is one of the equations or the condition for the light to have constructive interference at a point P. Is this clear to you? You will
Yes,
have to
teacher.
memorize this equation. A sin theta is equal to n lambda. Whenever there is a constructive interference, or for the nth constructive interference or the nth bright fringe, the condition is that A sin theta is equal to n lambda. Is this part clear to you? Can I continue?
Then and lambda means SB to right? S to B.
S2B. S2B. N lambda is S2B. S2B is the
Yes.
path difference.
That
So,
difference. Yes.
yeah,
Got it.
for constructive interference to occur, yesterday we derived that the condition is that the path difference should be equal to N lambda.
And lambda.
So we have
Got it.
derived this equation yesterday. So that is how we got this equation. Now let us continue. Now here you can see this distance is d, right? Let me assume a line here from here to here, that is from this center. Let me mark it as a point A. AO is D. AP is the line connecting the center of the two slits and the point P where we have a bright fringe. Now this angle theta in between AO and AP. Consider this angle theta. Now, we know that this line AO is perpendicular to S1, S2. AO and S1, S2 are perpendicular to each other. Also, we know that this is like a wavefront. S1B is like a wavefront which is perpendicular to the ray of lights. Now, we can make this approximation because this distance A is very small compared to this distance D. Here, A, the distance between two slits will be less than a millimeter. And the distance between the sources and the screen will be around 1 meter. So, see, this is around 1,000 times less than this distance. So, this distance A is very small and also Xn will be very small. So, we can assume that this line is perpendicular to both AP and S2P. So, this lines are perpendicular.
Can you repeat again? I mean, perpendicular. Which one is perpendicular?
Like
Parallel, right?
perpendicular, I am telling. AO. This line AO and S1, S2 are perpendicular to each other. Is that clear?
Yes, teacher, that's clear.
Yes. Now, I am telling that AP, this line AP and S1B are perpendicular to each other. We know that this S1B is perpendicular to S2P, right?
Yeah.
This
Yes.
difference between S2P, AP and S1P are very small compared to this distance because A is less than a millimeter while D will be 1 meter, around 1 meter, which means this A is 1000 times small compared to this distance. So I can assume that this S1B is a line which is perpendicular to both S2P and also to AP because they are almost same. This distance is very small.
Okay, like you were saying that the wavefront is
Yeah, like the
perpendicular to
wavelength
the
is
AP.
perpendicular to the ray of lights.
Yeah, got it, got it.
So wavefronts are perpendicular to the ray of lights. Like that, we can assume this is perpendicular. So we got this line AO perpendicular to S1, S2 and AP perpendicular to S1B, the angle between these two will be equal to the angle between these two. So thetas are equal. That's what I wanted to tell. So these angles thetas are equal to each other. So let me take the triangle APO. From triangle APO, that triangle, I can write tan theta. Tan theta means opposite side by hypotenuse. So what is opposite side? Opposite side is OP, which is xn. So I can write the opposite side is xn, which is OP, divided by the adjacent side. Sorry, opposite side by adjacent side because it is tan theta. So adjacent side is AO, which is D. So tan theta is equal to xn divided by D. Now this theta angle will be very small because this distance A is very small compared to D. So the angle will be very small, nearly equal to 0. So when the angles are approximately equal to 0, very small, we may assume that if theta is very small or theta is less, very small, we can assume that sine theta is approximately equal to tan theta. What is sine 0? 0. What is tan 0? 0. And sine goes to its maximum value from 0 to 90. And tan goes also from 0 to 45 by 45 degree, it will become 1. So in the beginning part, when the angle is very near to 0, that is when the angle is very small, we can assume that sine theta is approximately equal to tan theta. We have here tan theta is equal to x1 xn by d and sine theta is equal to n lambda by a. So I am taking this approximation here. So when I take this approximation, I can write instead of sine theta, n lambda by a is equal to tan theta is xn divided by d. Or in other words, I can write xn is equal to n lambda into d divided by a. Here I have taken d to the other side, so it goes to the numerator. So this is for the nth bright fringe. So xn is the distance from O to the nth bright fringe. Is this clear to you how I got this xn?
Yes, teacher, clear.
It's clear. Okay. Now this is for the nth bright fringe. What about the n minus 1th bright fringe? Suppose we have another bright fringe at a point Q, and that is the n minus 1th bright fringe. And the distance between O and Q is xn minus, okay, is equal to xn minus 1.
That's for even or odd?
It will be even, means bright fringe. At P we have a bright fringe. Now at Q also we have bright fringe. We know from here there will be a bright fringe, a dark fringe, a bright fringe, a dark fringe, like that. So let P
So
be,
if xn is bright one, so xn minus 1 should be the dark one, right?
I'm considering Q also as the bright fringe.
Okay.
For example, suppose this is a 7th bright fringe. Suppose it's a 7th bright fringe. Okay.
And that Q is
Below
fixed
that
one.
there will be the 6th dark fringe. Below
Yes.
that there will be the 6th bright fringe. Then 5th dark fringe. Like that it will go, right? So I am assuming that P and Q are bright fringes.
Okay.
P is the nth bright fringe, Q is the n minus 1th bright fringe. The bright fringe just before P. Is that clear now?
Yes, teacher.
Q also is a bright fringe. In between them, there will be a dark fringe. So I will draw again the dark and bright fringes. So this is the xn nth bright fringe. So I can write xn minus 1 will be equal to, instead of n, you just have to put n minus 1. So n minus 1 into lambda d by a. That will be the distance between O and Q. So you got two equations. One is the distance from the sender to the nth bright fringe. Second is the distance from the sender to the n minus 1th bright fringe. Is this part clear to you?
Yeah, you just replace the value of n, nothing else.
Yeah. Just we have changed the value of n to n minus 1. If this here n was 7, this will be 6. That's all.
6.
So let me rub this part and draw the fringes so that it will be clear to you. So let me rub this part. I will require these two equations, so I am keeping it as such. Now, here I would like to draw the fringes which we will see here, and I will put points so it will be, I hope it will be more clear to you. Suppose this is a bright fringe. Assume it is the sender bright fringe. Sorry, this is a dark fringe, right? So this is a dark fringe you have. Here you have a bright fringe. Here you have another dark fringe. I cannot draw a bright fringe only if I put a line like this. Assume this is a bright fringe, this is a dark fringe, and here again I have a bright fringe, then a dark fringe. I'll shade it. Okay, then a dark fringe, then again I have a bright fringe, a dark fringe. Like that it will continue. So I'm assuming if this is the sender, if this is the point P, I have taken a bright fringe. And just before P, Q, that is another bright fringe. So this distance I have taken, this is supposed to be a straight line. Okay. So here I have these points P here and Q here. So here the distance from, if this is O, this distance is xn up to P. Okay, and this distance is x minus 1 from 0 O to Q. Is that clear now? Now we want to find the separation between two consecutive fringes. P and Q are two consecutive fringes. So how can we find the distance between two consecutive fringes? It will be the distance between the points P and Q, right? So we know xn and we know xn minus 1. So to find the separation between two consecutive fringes represented by delta x, I can take it as xn minus xn minus 1. Is that clear?
Yeah, just the difference, right?
What?
Just the difference between the two points.
The separation between two consecutive fringes. So the distance between two consecutive fringes, that is the distance between P and Q, let me express it as delta x. So separation between two consecutive fringes. Consecutive means nearby fringes. Now here we have taken two bright fringes. So delta x will be equal to xn minus 1. So I can substitute this for xn and this for xn minus 1. So I will get this as equal to n lambda d by a minus n minus 1 lambda d by a. So if I expand this n minus 1, take it to lambda d by a, you will get it as n lambda d by a minus n lambda d by a. I'm expanding those brackets. So minus times minus, it will be plus lambda d by a. So n lambda d by a minus n lambda d by a, they gets cancelled. So what remains is lambda d by a. So I have delta x, or the separation between two consecutive fringes, is equal to lambda d by a. What is lambda? What is lambda?
Wavelength.
Wavelength,
Wavelength. What is d? Capital D?
the distance between the source and the
Screen.
screen.
Source and the screen. And what is A? A is the distance between the two sources. So this is the separation between two consecutive fringes. Now, this is the separation between two consecutive fringes, right? Now, if I take this point and this point, it will be same, right? PQ I have just moved to the bottom of this consecutive bright fringe to the bottom of this bright fringe. So this distance also will be equal to delta x, right? Now fringe width. Fringe width refers to the width of one fringe, either bright or dark. So this distance is called fringe width. Fringe width. This distance. How can I find fringe width?
By dividing delta x by 2.
Yes, just I have to divide delta x by 2. So the fringe width in your textbooks, the expression for fringe width is delta x is equal to this divided by 2. That is lambda d by 2a. So this is the fringe width. Now here, I want to clarify something. I have used here all the symbols or expressions given in your textbook. But if you refer to other textbooks or if you refer to some materials, usually these distances are expressed as yn because it is in the vertical direction. So yn minus 1 like that. And in some material, they refer to the separation between two consecutive fringes itself as fringe width. I have seen such material, so don't get confused with that. That's why I wanted to mention it here. And in most of the books, the fringe width is represented by the symbol beta. So don't get confused. Once the concept is clear to you, you can see here. And in those books where they consider the separation between two consecutive fringes as fringe width, I always noted that they take the distance between two of the slits as 2a. So they will end up with the same equation. So don't get confused when you see this somewhere something like that. Okay, so but stick to this concept, it is very clear. Stick to what is given in your textbook, it is very clear. So is it clear to you how we got fringe width?
Yes, teacher, clear.
And you have to remember this formula, fringe width is lambda d by 2e. And note, the separation between two consecutive fringes here is not the fringe width. Fringe width is just half of that. Now, what I'm going to do is, we will look into this equation, analyze this equation, and try to learn more about the fringes. So let me rub all this derivation and let me focus on this equation alone, the equation for fringe width, which is equal to lambda d by 2a. So let me rub all of them. So I'll still keep this figure, and then let us consider this equation for fringe width. Delta x is equal to lambda d by 2a. Let us look into this equation and learn more about the fringes. What this equation can tell us about the fringes. The first point to be noted is that, is there n in this? N,
No.
the order of the fringe, it is not there, which means all
It doesn't depend.
fringes will have the same width. So if you see the interference pattern, you will not be able to notice which is the central one. Okay, all fringes will have the same width, either dark or bright. We didn't think that it should be the bright fringe. We derived the expression for separation between two consecutive fringes. We didn't specify it is the two consecutive bright fringes or dark fringes, even though we considered bright fringes for the derivation. So all the fringes, bright or dark, will have the same width, since n is not there in this equation. So all fringes have same width. That is first point to be noted from this equation. Let us see the next point to be noted from this equation. Here, the fringe width is proportional to lambda. So the width of the fringe depends upon the wavelength. It is proportional to lambda, which means the larger the wavelength of light, more will be the fringe width. Now this fringe width is very small. It will be less than a millimeter. So it is very hard to observe through our naked eye. Often we use a microscope to observe the interference fringes. Now let me ask you something. Which one will be? Okay. So which one will be more clear if I use red light or blue light?
Red, right?
Red. Why?
Because it has more wavelength.
It has more wavelength. So the fringe width will be more and more observable compared to blue light. So more the wavelength, more will be the fringe width and more resolution it will be having. So that is the second point to be noted. And let us assume what is the third point to be noted. See, the fringe width is directly proportional to D. Delta x is proportional to D. So if you keep the screen at a further distance from the sources, you can see more fringe width or you can see it more clearly. That is why in the beginning itself, I told that one of the conditions to see interference pattern is that D should be very large compared to the distance between the two sources. So that is another condition, that fringe width should be or the screen should be kept at a large distance. Larger the screen distance from the sources, more clear or more will be the fringe width. Now the fourth point to be noted is that the fringe width is inversely proportional to A. What is A?
Distance between two sources.
Yeah, A is the distance between two sources. A is the distance between the two sources or two slits. So we can put delta x is inversely proportional to A. So here the distance between the two sources should be very small. Only then we will get a good fringe width and it will be observable. So lesser the distance between the sources, more will be the fringe width. Now another point to be noted is that whenever light enters from one medium to another, what happens to its velocity? Its velocity changes, right? Suppose light enters from air to water. What happens to its velocity?
Decreases.
It decreases, you know that. Now, velocity of light depends upon two quantities, that is wavelength and frequency. So, when light enters from air to water, one of this should change, right? Which one changes? Is it the frequency or the wavelength?
Wavelength.
Wavelength changes. The frequency will remain the same. So, in different media, the wavelength is different. So, the Young's double slit experiment, we assume that it is conducted in air or in vacuum. But if the same experiment is conducted in a medium having refractive index mu, the wavelength will be different. So the wavelength of the same light in a different medium having refractive index. See, the wavelength in the medium is equal to wavelength in air or in vacuum divided by the refractive index of the medium. So the wavelength of a light in any medium is equal to wavelength of the light in air or vacuum divided by refractive index of the medium. So the wavelength decreases when it enters to another medium, or if the experiment is conducted in another medium, the wavelength is lesser. So when the wavelength is lesser, what happens to the fringe width? When the wavelength is lesser, what happens to the fringe width?
It is also less.
It is also less. So the fringes become more closely spaced if you move the whole apparatus for Young's double slit to another medium, a different medium than vacuum. And more the refractive index of the medium, more closely the fringes will be. The fringe width will be less because the wavelength will be less. Now, another thing, suppose you are placing in the path of one of the rays a small plate having thickness T and refractive index mu. Let me draw the diagram again. Here you have the slits S1 and S2, and you have a screen here at a distance D, and we assume that they meet at a point, say P. Now, in one of these rays path, we are placing a thin plate or a plate of thickness T. Okay, so it has to travel through another distance T through a medium. Suppose this plate have a refractive index mu. We are placing in the path of one of the rays a thin plate having thickness T. Then what happens is additional path difference will appear for this ray, and the additional path difference is mu minus 1 times T, where mu is the refractive index of the plate and T is the thickness of the plate. So mu minus 1 into T. So that is the quantity of path difference which is introduced in one of the rays. You need not go into the mathematical details of that, but you just understand in such a case, there will be no change for the fringe width. But all the fringes together will move towards the side where this plate is kept. In this case, the plate is kept on the ray coming from above or top. So all the fringes will move a small distance up, but there will be no change in the fringe width. Is that clear to you? So these
Because
are,
the medium is not changed, right?
yeah, medium is not changed.
It's just
It's
an
still in
difference in the
vacuum.
path.
Yeah, we just introduced an additional plate having thickness T. So what happens is the path difference will be different. One of the ray will have an additional path of mu minus 1 times T. And as a result, the whole fringe will move a little up, but the fringe width will remain the same. So these are some of the discussions I would like to have related to this equation so that we can know more about the interference fringes. So that's all what I wanted to discuss today. And in the next
Teacher,
class, we will see diffraction of light.
teacher,